We're going to take a look at this problem. At 2 pounds per minute of air comes into a dehumidifier at 70 degrees Fahrenheit and 80% relative humidity. The air is cooled to 40 degrees Fahrenheit. The air is then heated to 75 degrees Fahrenheit. Do the following and find the following. Show the process, the initial, intermediate, and final states on a psychrometric chart, and mark each state and its associated properties. Find the temperature just as the moisture starts to condense. Find the specific humidity after the cooling process. Find the rate of heat transfer required to heat it from 40 degrees to 75 degrees. Find the relative humidity at the final state, which is 75 degrees, and find the specific humidity also at the final state, 75 degrees. So we have a picture something like this. The air coming into the dehumidifier. Again, it's being cooled, and also as it's once it gets to a certain point, moisture starts dropping out, and it continues to be cooled. So this is, let's say, the inlet, and then this would be like, say, when it gets to the dew point, and this state part three is at the end of the whole cooling process. And we're told it's going to be 40 degrees at that point, and then the air is going to be heated and come out at 75 degrees. Again, it's being cooled here and heated here. We take a look at this in a psychrometric chart. We have at the beginning 70 degrees and 80% relative humidity. I don't know if it's very easy to see on this. So we come 70 up to 80% is going to be this point right here. And that's our starting point when the air comes into the dehumidifier. And then it's going to be cooled. So that means we're going to just go to the left until we hit the saturation line. So we go to the left to the saturation line. And then we continue to cool. Notice we hit the saturation line at about between 60 and 65 degrees. We're at about maybe 63 degrees. And then we continue to cool. We want to cool all the way down to 40. So we'll continue along the saturation line because moisture is going to be dropping out, water is going to be dropping out because we're cooling all along the saturation line. And we're cooling all the way down to 40 degrees, which is this line right here. It doesn't seem to be marked up here, but you can see that's 40. So this is here is going to be our state one. This is state two, where it starts hitting the saturation line. Then state three is when the final cooling is going to be done. Then finally, we're going to heat the air, and that means we're going to go horizontally to the right until we get to the 75-degree line. And notice here's the 75-degree line here. Get to that point right there. Our final state four, I'm going to put the 4 up here because it's going to be a little bit crowded down there, like that. So we'll from 1 to 2 along the saturation line to 3. and then up to 4, like that. And we want the temperature, it says just as the moisture starts to condense. That was one of our questions. Find the temperature just as the moisture starts to condense. And we can see that that's going to be, as we said here, about 63 degrees. So part B, the answer is going to be 63 degrees Fahrenheit. And then we want the specific humidity after the cooling process. And so the cooling process goes all the way down here. Now the specific humidity is all the way to the right, so we're going to have to zoom out a little bit here. So we go to the right, and we have to make a line that looks like, again, we're between 0.0043 and 0.0057. We can maybe estimate about 0.0047, maybe. That's just a guess. And so that's part C. Again, specific humidity is omega. And that was 0.0047 pounds of water per pound of air. And the next thing we want to find is the rate of heat transfer required to heat the air from 40 degrees to 75 degrees. Now we're going to need the enthalpy in order to do that. And so we'll have to find the enthalpy, again, for the heating process. So remember, enthalpies are these lines here. So we have to follow these lines to find the enthalpy. So like it's say state 3, actually this falls right at 15. And those, of course, BTUs per pound. Right at this process. Again, we follow this line up to here. And then also we want to, after the heating process, so that would be this point here. Again, follow that enthalpy line. And again, it's going to be parallel to this other enthalpy line over here. And it looks like we're landing about right there. If this is 20, let me extend that out a little bit. You can see this one is 20. That's 25. This looks like 1, 2, 23.2 maybe. Like that. But we're also going to need to remember that the mass flow rate, the total, is the mass of the air plus the mass flow rate of the water vapor. And remember, we can actually factor out the MA, and we could say something like this. And we can just verify that this is the same expression. MA times this gives us MA. MA times this, the MA's cancel, and we get mass flow rate of the water vapor. Now, of course, this is the specific humidity. Again, the specific humidity is the same as the humidity ratio, this omega up here. So we can we can make the mass flow rate equal to MA this, mass flow rate of the air, plus the specific humidity or the humidity ratio. And then we can use this to solve for MA. Like this. And then calculate the heat transfer rate. Minus H3. I called the final state H4. And when the heating began was H3. And we just found those on the chart here, 15 and 23.2. That's BTUs per pound mass. And we're going to replace the mass flow rate of the air with this. And so we're putting that in here. And so we're going to put the total mass flow rate, which was 2 pounds per minute, divided by 1 plus the specific humidity. And all through the heating process, the specific humidity is going to be this, because the heating process occurs along here, and we found the specific humidity there, which was at 0.0. We estimated it was like around 0.0047. This, and we can put this into our calculator. 16.32, and the pounds cancel. This ends up being dimensionless. So we have BTUs per minute, like this. Or if you multiply that by 60, that gives us something like 979 BTUs per hour, like this. Now, the relative humidity at the final state, we can get that right from our graph. And the final state was this point right here. And we can just read it. And here it's going to be between 20 and 30% relative humidity, somewhere in between this curve and this curve, 20, so down to maybe 27%, 28%. I'm going to estimate 27%. We're going to estimate that. And then finally, the specific humidity at the final state, that would be at this. And actually, notice the specific humidity at the final state is going to be the same as the specific humidity at state 3, because it would not have changed, because the specific humidity, again, or called the humidity ratio, is over here. And so those are going to both be the same. So whatever we found for part C is going to be the same. So for part C, we found that that was 0.0047. So there's all of our answers. And again, there's the whole process on the chart. Cold, cold, heated. All along this region here, moisture is dropping out because we're at the saturation line.